Hello, hello, hello. In this episode of What's the Big Idea, we're going to be talking about Newton's law, Newton's second law, for rotating objects. Newton's second law, of course, has played a central role so far in Physics 107 for describing the motion of objects that could be treated as particles. And now we're going to extend our discussion to consider rigid bodies that can rotate, and we want to find out what is the version of Newton's second law that we can employ when trying to think about the motion of rotating solid objects. So, in honor of the impending baseball season, I'd like to start off the discussion in an unlikely place with a clip from a movie which maybe you've seen, but somehow it wouldn't be surprised me if none of you have seen it. This is a movie that came out in 1992 called A League of Their Own, and as you'll see in a minute, it features not only Gina Davis and Tom Hanks, who are the sort of the stars of the movie, but uh, Rosie O'Donnell and Madonna. And Rosie O'Donnell, who you've probably heard of, was the first movie that she ever appeared in, and Madonna was a verifiable star in 1992 when this movie was made. I'm mentioning all this because this is a movie. My daughter was an avid baseball player when she was a kid, and this movie was very inspirational to her. And I have undoubtedly seen this movie well over 100 times, so I can't resist showing you a scene from it that has something to do with today's discussion. So let's enjoy a clip from A League of Their Own.
Hey, mate,
What?
come here and look at this.
Wait a second, Doris.
I can't wait much longer, so get up. Yes, so. Here, so I ain't done yet. Watch this.
That's it?
Yeah, you can't do it, mate.
Do it. I could do it. Yeah, how long you been working on it, Doris?
That took me about a year. Not counting them 2 months I was in the hospital, bat hit me right in the head. Bam.
Okay, so admittedly, the connection to rigid body rotation is a tenuous one, but there is this issue of how do you balance a baseball bat on your fingertips and what's the best way to do it? And that is a question that we will answer in this exciting episode of What's the Big Idea? So let's dig in. So, for this discussion, we'll confine ourselves to consideration of objects in which the direction of the axis of rotation remains fixed. So, I want you to imagine that this is something like a bicycle wheel, and the axis of the bicycle wheel, the axis upon which it can rotate, is coming out of the plane of the screen that you're looking at. And so, this object is free to rotate either counterclockwise, the way this arrow indicates, or clockwise. And we can specify the position, the angular position of the bike wheel at any point in time with an angle theta. So you have some reference point P on the bike wheel, and theta represents the angular position. And really, by constraining ourselves to the situation where the axis of rotation is in a fixed direction, it's really very similar to the way we started off with kinematics of an object which is constrained to move in one direction. So we started off the course by talking about objects that could just move in a straight line, and we characterized their position by a variable x. Well, theta is playing the same role. It's a quantity which can either be positive or negative and specifies the angular position of the bike wheel. Theta is the angular position, and we can define the quantity omega, which we're going to call the angular velocity, is simply the rate at which the angular position is changing. So very analogous to what we saw with one-dimensional kinematics, where the velocity is either a positive or a negative number, but it's not a vector quantity here. And we can just play the same game, differentiating one more time. We can have a angular acceleration, very analogous to the linear acceleration that you've seen previously. in one dimension, and the angular acceleration is just by definition d omega dt. And we've previously shown in an episode of What's the Big Idea that if you consider the kinetic energy of such a spinning object, we can write the kinetic energy of such a spinning object as 1/2 I omega squared. So this is a relationship that's very analogous to the 1/2 mv squared relationship for the kinetic energy of a particle. And now we see omega is playing the angular velocity takes the role of v, the linear velocity, and this quantity I, the rotational inertia, is playing the role of mass. Okay, and that's a game that something you're going to see repeatedly is that in this rotational world, when we consider rotating objects, the quantities that we define are often, and equations that we use are often have a direct analog to something that you've seen just in the language that we use to describe the motion of particles. But now, what's differentiating the bodies that we're considering now is that unlike a particle in which there's a distinct velocity that the particle moves at, when you have a rotating object like this, different parts of it are moving at different velocities. Parts on the rim are moving faster than parts in the interior, for example. So that introduces a complication. But the nice thing about quantities like omega and alpha is that those are going to be the same for every single point on the wheel. The wheel as a whole is going to be characterized by its angular velocity and its angular acceleration. And that is an enormous simplification. Okay, so now let's move forward. We want to talk about Newton's second law. And Newton's second law for a particle, which we said has played such a central role in our discussion, it says that the acceleration of the particle just depends, and again, this is in one-dimensional motion, so I'm not bothering putting vector signs on. The acceleration of the particle is just proportional to the mass of to the force acting on the particle and inversely proportional to the mass of the particle. So that's Newton's second law for a particle. What is the version of Newton's second law for a rotating body? That is the question that is on the table. Newton's second law for a rotating body. Well, we might guess, and this is just a guess at this point, but if we're talking about analogs, the thing that's going to be analogous to the acceleration is likely to be the angular acceleration, and the thing that's likely to be analogous to the mass of the particle is going to be the rotational inertia of the object. And then the question mark that remains is what do we put in the numerator here? What is the rotational analog to the force? In other words, forces cause an object to accelerate. How do we quantify or describe the thing that causes an object to have an angular acceleration? Okay, so to begin to answer that question, I'd like to consider the following simple situation. Imagine I have a point mass, m, that is attached to a rigid rod, indicated by this black line, and rod has essentially no mass, and that rod is attached to an axis here, and such that the mass is free to rotate about this axis so that its angular position theta is free to change. So it's going to move, the mass is going to move around in a circle. Now, what's going to cause it to move? Well, we're going to imagine that we apply some force to the mass. And the force can go off in any direction, I suppose. But in this discussion, so we'll call that F, but in this discussion, we're really just concerned about what's happening in the tangential direction. So I'm going to call the tangential component of this force F, F sub t. And that's going to be the force, as you know, that's responsible for the tangential acceleration, which is the rate at which the speed or rather, I should say, the magnitude of the velocity of the mass is going to change. So Newton's second law, if we're going to focus just on what's happening in the tangential direction, can be written that the tangential component of the acceleration is just equal to the tangential component of the force divided by the mass. And the tangential component of the acceleration is just dv dt. So that's equal to the tangential component of the force divided by the mass. Now, recall, we've previously shown that there's a connection between the velocity v in the tangential direction and omega. So we can rewrite v as omega times r. And because r is a constant in this story, we can pull it out of the derivative and write the left-hand side as r times d omega dt. And that's equal to ft over m. And of course, d omega dt is just alpha, the angular acceleration, over m. And then I'm just going to divide both sides by r, and we have that the angular acceleration is equal to the tangential component of the force divided by the mass times r. Now we're almost there, because remember where we were headed. We wanted to express something that looked like Newton's second law, and we had something of the form that the angular acceleration was equal to something over I. So to get there, all I need to do is to multiply both the numerator and the denominator of the right-hand side by r, and we have that the angular acceleration is equal to the tangential component of the force times r divided by mr squared. And of course, mr squared is just the rotational inertia of the object. So we've shown that we can write the angular acceleration is just this quantity ft times r divided by I. So I can write the angular acceleration is just equal to a quantity that we're going to call the torque divided by I, where the torque is by definition the tangential component of the force times the radial distance r. And this boxed equation is going to represent what we're going to refer to as the rotational analog to Newton's second law. And this quantity that we're calling the torque, and I should write out the word torque, the torque is going to be the rotational analog to the force. And just to bring this discussion into alignment with the notation that Wilson uses, we can call what I've been calling F sub t, the tangential component of the force, F sub perpendicular. It's the component of the force perpendicular to the r. R is a vector which points from the axis of rotation to the place where you're applying the force. And F perp is a component F that's perpendicular. Wilson writes this, he defines an angle in this picture which he calls theta. That's this angle here. Theta has nothing to do with the angular position of say, a bike wheel or anything. So we're using theta to mean two completely different things. So that's one source of confusion. And if that angle is theta, then this angle in here is 90 minus theta. So we can write the torque as F perp is just F times cosine of 90 minus theta times R. But that's equal to cosine of 90 minus theta is the sine of theta. So he writes the torque as F times R times the sine of theta. And if you really want to develop an intuition as to what's going on with torque here, I suggest you go to a door. So I'm going to draw a door. Here's the hinge of the door. And I'm going to give sort of a top view of the door. So we're looking down on the edge of the door. And if you wanted to open the door around this hinge by pushing on it, say, that's where you can begin to develop an intuition of torque, because torque is going to be the sort of the entity that causes the door to open. So if you want to, if you push very close to the hinge, if you apply a force here, it's not going to be nearly as effective as if you push far away. So that's because we can say now, when you push farther away from the hinge, R is greater, and therefore you're exerting a greater torque. Not only that, but you got to get the angle right. Really, the optimal angle to press is perpendicular to the door, which actually that makes theta equal to 90 degrees, and that's maximizes the torque. If you come and you push at some odd non-perpendicular angle, that's going to lead uh, to you being less effective in opening the door because you're exerting less torque. So as a test, with this definition of torque here, the question I want you to think about is which is the best situation for trying to, I guess in this case, tighten a nut, because you're trying to exert the most torque. So which uh, uh, of the four situations, or how would you rank the situations in terms of the torque being applied to the nut here? You should press pause and think about that for a second, and then we'll resume. Okay, so to help answer it, let me simplify things by pointing out, let's call the length of the wrench R. So in situation one, the torque, the tangential component of the force is just the force itself, and the radial distance to where the force is being applied is R. So the torque in case one is just F times R. In case two, the tangential component of the force is still F, but now the distance in which it's being applied, the radial distance, is much greater. Maybe that's something like 3 times R because of that long rod there. In case three, the torque is the tangential component of the force is going to be this length here. And so the torque is going to be less than F times R. Whoops, that's an R. And finally, in case four, the torque is just going to be equal to F times R because the tangential component of the force is still F, and the force is really being applied at this case at this point. The rod, the horizontal rod here, doesn't do anything to change the force that's being applied to the end of the wrench. So what we see then is that the correct answer is um, C, because case two is the biggest. 4 and 1 have the same torque, and 3 has the least torque. Okay, let's get back to our expression for the rotational analog of Newton's second law and see what that has to do with balancing a baseball bat on your fingertip. Okay, so here's the idea. I'm going to consider the act of trying to balance an object on my fingertip here. And instead of starting with the baseball bat, let's consider two extreme cases. Let's imagine there is a massless rod with a point mass m, and the point mass can either be very high, very far distance from your fingertip, or a very small distance from your fingertip. So the distance from the mass to your fingertip, we're going to call h. So just to leap ahead, this situation is going to be analogous to when you try to balance, when Rosie O'Donnell tried to balance the baseball bat with the wide end, where most of the mass is at the top. And the other case is when most of the mass is at the bottom, when you have the bat upside down. And the question is, which is easier to balance when you have the mass up high or when it's low and close to your fingertip? And the answer, if you haven't tried this, may surprise you. But it's not surprising if you use this discussion of the rotational analog to Newton's second law. So we're going to start with alpha equals torque over the rotational inertia. And if we just have all of our mass in a point mass, then the rotational inertia is just going to be given by mh squared. And the torque in this case, the thing that is causing the bat to rotate about my fingertip, is the torque due to gravity. Gravity is exerting a force, and it's being exerted at the point mass, and it's pointing straight down. And the expression, therefore, for the torque is going to be the tangential component of gravity. So we want to know the component of gravity that's uh, uh, basically perpendicular to the rod. That's the one that is going to cause a torque. And the tangential component of a torque is the tangential component of gravity, which is going to be mg sine theta, where theta is the angle that the rod has tipped away from vertical. So the component of gravity that is tangent, that is, in other words, perpendicular to the end of the rod, is just going to be mg times sine theta. And then we just have to multiply that by the distance h, because the way we get torque is the tangential component of the force times the distance between where the force is being applied and where the axis of rotation is, which is this distance h here, or this distance h here. And what do we get? Well, the m's cancel, and we get a factor of g sine theta, and there's h over h squared, and that just gives a factor of h. So what does that mean? That means that the smaller h is, the greater the angular acceleration. And when you go to balance something, having a big angular acceleration, if you tip it, is really what's a killer. Because the way you can balance something is if it starts tipping a little bit, you need to be able to quickly adjust your finger and move it so that you can counteract the fact that it's tipping. And if you have a big angular acceleration, once it starts tipping, things go from bad to worse very quickly, and you don't have time to respond. So the thing that's going to make it easiest to balance is when you have a small angular acceleration. And that ends up being, as you can see from this argument, when h is as big as possible, which means when the mass is concentrated at the top. So we tend to think of having mass up high as being unstable, but in fact, it's just the opposite. And we can demonstrate this. I will demonstrate this to you experimentally on the next slide. Okay, so let's watch this
So I'm
demo.
going to try to balance the bat on the tip of my finger, and first I'm going to do it with the mass up high, and that's actually pretty easy because the angular acceleration is pretty small and my finger can adjust. But when I try to do it upside down, it's nearly impossible. So
That's it for this episode of What's the Big Idea? Hope to see you again soon. Bye bye.